The answer is not 1/2 class period. So that's why I'm not just switching, because I've tried that before when I didn't have time to recharge the batteries. And then Russell gets to see me say something like, and so the most important part of today's lecture is this. If there's one thing I want you to take away with you, it's, something like that. So the killer is, so. All right. Now let's show something very important, which is that the matrix corresponding to the product of two operators is what we would hope the product of the corresponding matrices. In other words, if you have two operators represented by matrices, then the matrix which represents their product is just the matrix product of those two matrices with one another. Is the product of the corresponding matrices. That this whole matrix business carries right on through. And to show that, we say, okay, I want to write an expression for the ijth element of the matrix representing the product of operators omega and lambda. Like any self-respecting matrix element, and even one that doesn't respect itself, that is going to be that inner product. I inner product with omega lambda, inner product, I'm sorry, J, inner product with J. Sometimes you get alphabet soup going here. Okay, so now here's where we're going to do something which at first sounds trivial, but it's incredibly useful. We're going to insert the identity operator in between those two operators. That doesn't change anything, because identity operators just say, I'm going to avoid you completely. So this is the same as I, omega capital I, lambda J. The identity operator's been inserted in between them. And at first you think, well, bully for you, let's do it 14 times. But no. What we're going to do is now use the fact that we can write the identity as a sum of projection operators. In other words, we're going to say that is the sum over k of I, omega, kk, lambda, j, using the fact that the identity operator can be written as the sum of the projection operators for each of the basis vectors. So the identity is the sum of the outer product of k basis ket with k basis bra. So I've inserted the identity and then expanded it as a sum of projection operators. We have inserted the identity, is what we call that. It turns out you do that all the time to prove things in linear algebra, in quantum mechanics. It's actually a very useful thing to do, because what would we call this inner product right here? The inner product of bra I, omega, and ket k. It's a matrix element, right? It's the ikth matrix element of omega. So this is omega sub ik, the ikth element of the matrix representing omega. And meanwhile, this is the kjth element of the matrix representing lambda. And we're done, because this is the rule for finding the element ij of the matrix representing the product of omega and lambda. This is the summation form of the rule for multiplying two matrices together, that the ijth element of the product is this summation. So we have completed the proof. And if you don't believe that, then it can be helpful to give an example. Or if you don't believe it or you're not sure, if I do omega 1, 1, omega 1, 2, omega 2, 1, omega 2, 2. So I just make a nice, simple 2 by 2 matrix. And same deal, lambda 1, 1, lambda 1, 2, lambda 2, 1, lambda 2, 2. If I multiply those two matrices together, I'm going to get another 2 by 2 matrix out. And we're not going to do the whole thing because that would be tedious, but let's look at just the upper left component. The upper left component is going to be omega 1, 1, lambda 1, 1, plus omega 1, 2, lambda 2, 1. Right? That's the rule for multiplying matrix. Dot the ith row with the jth column to get the ijth entry. So this will be omega 1, 1, lambda 1, 1, plus omega 1, 2, lambda 2, 1, etc., etc., etc. So notice that omega lambda, the product 1, 1 entry, is in fact omega 1, is in fact the sum over k of omega 1k lambda k1. In other words, it fits that pattern that we have over here. Omega lambda 1, 1 is the sum over k of omega 1k lambda k1. That's what this is. Omega 1, 1, lambda 1, 1, plus omega 1, 2, lambda 2, 1. And you can do that for every entry, if you don't believe it already, and convince yourself that the pattern always works, so that this is the summation version of how you multiply two matrices together. This is the rule that tells you the ijth element of the matrix product of matrices omega and lambda. And in fact, in linear algebra, many, many proofs involve doing these kinds of tricks, doing summations like this, and recognizing matrix products in the summations. That's how you make these general proofs for arbitrary number of dimensions, as opposed to, it'd be ridiculous to try to write out matrices in general terms and blah, 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 blah. It's much easier to do summation notation. So, any questions? I'm hot. By which I mean, the temperature is getting high in here. I'm not Paris Hill. I'm Paris Hill. That's hot. Right.
Well, at least you're not free.
Yeah. I don't really want to be Paris Hill. But anyway. Okay. So
just keep in mind now this is being recorded for posterity.
Yeah, that's true. That's true. Yeah. Well, I caught endless grief because the Jeopardy, the Wins Jeopardy. One year there used to be physics and math CS were allied, and so Sean and I were allies along with the rest of our departments. And boy, we just went all the time. And so, oh yeah.
What did you guys win? You guys won 5 times.
Oh, we won multiple times in a row.
I feel like just physics and like math.
Physics, math, CS, we were just winning.
Yeah, you guys won.
Yeah, so they split us up because everybody knew that nobody could defeat our combined forces. So anyway, it was like maybe the first or second time they had the Jeopardy. And one of the questions was something about some celebrity who had a sex tape or whatever. And then I knew the answer was, well, Sean pokes me and says, Paris Hilton. I said, I know. So, Paris Hilton. I never caught the end of it of people saying, oh, you know all about Paris Hilton and all this kind of stuff. It's like, well, everybody knows that. We just had quicker fingers. But, so, I can't stand her, and that made me even just like, yeah. Anyway, so, and no, I haven't seen it, by the way. I have no interest in seeing that. I don't look at that sort of thing. Anyway. Just to clarify. So anyway, any questions? All right. So that's convenient. Products of matrices are the matrices that represent products of operators. Yay. Now let's talk about the adjoint of an operator. We found the adjoint of bras and cats. Let's talk about the adjoint of an operator. You will recall that the bra corresponding to alpha times ket V, which we somewhat sloppily indicate as ket alpha V, and again we have to use different alphabets. Unfortunately, your book in its Appendix A and all that uses Greek letters to denote cats and bras, and I'm using them to denote scalars. Yeah, whatever. You got to get used to seeing different notations. In the book, cats are represented like alpha, beta. Scalars are like A and B and stuff like that. Whereas I'm using capital letters. Capital